Welcome to Podcast Learnin' Fun. Let's start today's journey of learning. Ever find yourself daydreaming about teleporting? Snapping your fingers and bam,
Yeah.
you're somewhere else.
Well, today, we're going to be talking about something kind of like that, but instead of teleporting people,
Oh, okay.
it's all about teleporting particles using something called the displacement operator.
Displacement operator, huh?
Yeah. It's a mathematical tool
Okay.
that lets us move particles around, but not in the way you might think. We're not talking about physically picking them up and moving them.
Gotcha. So where are we moving them?
We're moving them in something called phase space.
Phase space. All right, now you've really lost me. What is that?
So imagine like a map, right?
Okay.
But instead of just showing a particle's location, it also shows its momentum, like a GPS that tells you not only where a car is, but also how fast it's going.
Okay, so it's like a more detailed map of a particle state.
Precisely. And the displacement operator lets us slide that particle around on this phase space map without actually changing its energy. So no teleportation in the sci-fi sense, just shifting possibilities.
So, no, like instantly beaming across the galaxy. Bummer.
Uh-huh.
But still sounds pretty cool. So this displacement operator,
Yeah.
is it like a cheat code that breaks the laws of physics or something?
Not at all, actually. It's very much within the laws of physics.
Okay, good to know.
One of the really interesting things about the displacement operator is that it's unitary. This means it's a reversible action.
Reversible, like hitting rewind on a video.
Exactly. If we use it to move a particle, we can always apply it in reverse to bring it back to its original state, like nothing ever happened.
A quantum rewind button, that's neat.
Mm-hmm.
Why is this reversibility so important, though? Does it affect how the particles behave?
It actually has huge implications for how we understand probabilities in quantum mechanics. So quantum mechanics is all about predicting the likelihood of a particle being in a certain state, right? And the displacement operator ensures that these probabilities stay consistent, even as we move the particle around in phase space. Think of it like shuffling a deck of cards. You change the order, but you still have the same 52 cards. Nothing's lost or created.
Okay, that makes sense. So we're not changing what the particle is, just exploring its potential.
Yeah.
I think I'm starting to get it. But I have a feeling there's more to this story, right?
Oh, there's definitely more. Let's bring in another concept. Imagine you have these controls that can increase or decrease a particle's energy.
Like volume knobs.
Exactly. And we call these controls raising and lowering operators.
Raising and lowering operators, got it. So like volume buttons for a particle's energy level?
Precisely. And this is where things start to get really interesting. The displacement operator works together with these raising and lowering operators.
Okay, I'm listening.
When we displace a particle, it affects these energy levels in a very specific way.
So we're not just moving the particle around, but also messing with its energy.
We're not messing with it, more like fine-tuning it.
Okay, fine-tuning it. So if we can manipulate these energy levels, can we actually change what a particle is capable of?
That's a great question, and it leads us to one of the most fascinating things we can do with the displacement operator. Let's consider the vacuum state. It's the state where there's no particle present at all, like the ground floor of quantum mechanics.
All right, you've got my attention. What happens if we apply the displacement operator to this nothingness? Does a particle just pop into existence?
Not exactly, but what we get is something equally remarkable. It's called a coherent state.
A coherent state. Okay, I'm intrigued, but clueless.
Hmm.
What in the quantum world is a coherent state?
Well, coherent states are sort of like a bridge between the strange world of quantum mechanics and the more familiar world of classical physics. They have this remarkable property. They behave in a predictable way.
Hold on. Predictable behavior in the quantum world. Isn't that like against the rule?
You could say that, but it's what makes coherent states so fascinating and important.
Okay, you've definitely piqued my curiosity. Can you give me an example of a coherent state? Something I can actually picture.
Absolutely. Think about a laser beam.
A laser.
It's incredibly focused, right? And its behavior is very predictable, unlike the usual fuzziness we see in the quantum world.
So you're saying that a laser beam is actually a coherent state?
Exactly. And that's just one example. Coherent states play a crucial role in many different areas of physics and technology.
Wow, I had no idea lasers were so deeply connected to the quantum world. This is already blowing my mind. We're just getting started. So you're saying by manipulating this nothingness, this vacuum state, we can create something that acts like a laser. That's wild.
It really is. And it highlights the incredible power of the displacement operator. It's like we're taking the fundamental building block of nothingness and using it to create something that bridges the gap between the quantum and classical worlds.
Okay, I think I'm starting to grasp the significance of these coherent states. But what makes them so special, besides this predictability thing? Why are they so important in physics?
Well, for one, they help us understand how the quantum world, with all its strangeness, can give rise to the familiar wave-like behavior we see in classical physics. Think about it. Waves are all about predictable oscillations, like the ripples on a pond.
Right.
Coherent states exhibit that same kind of predictable behavior, even though they're made up of quantum particles.
So they're kind of like a missing link between the two worlds?
You could say that. And they have practical implications, too, not just theoretical ones.
Okay, now you're talking. What kind of practical applications do coherent states have?
Well, for starters, they're the backbone of laser technology.
Wait, really? Lasers are based on coherent states?
Absolutely. Lasers rely on the predictable, focused behavior of coherent light, and that behavior comes directly from the properties of these special quantum states.
So, by understanding this displacement operator and how it generates coherent states, we're essentially unlocking the secrets behind some of the most important technologies we use today.
Exactly. And lasers are just one example. Coherent states also play a role in things like superconductivity and quantum computing, which are fields with immense potential for the future.
Quantum computing. Now, that's a topic I'd love to dive into sometime, but let's stick with the displacement operator for now. You mentioned it's also a key player in something called quantum state engineering.
Oh, yeah.
Quantum state engineering, it sounds like we're entering science fiction territory here. What does that even mean?
Well, it might sound futuristic, but it's a very real field of research. Think of it like sculpting with quantum particles.
Sculpting with particles. Okay, now I'm really intrigued.
Instead of just passively observing quantum states, we're actively creating and manipulating them.
Like we're quantum artists.
In a way, yes, we're using tools like the displacement operator to shape these states and give them specific properties.
So what kind of tools do we have in this quantum art studio?
Well, the displacement operator is one of our most versatile tools. It allows us to shift and modify these states with incredible precision. For example, we can create something called squeezed states.
Squeezed states. I've never heard of those. What are they?
Imagine you have a balloon, right?
Okay.
And you squeeze it. What happens?
It gets narrower in one direction, but it bulges out in the other.
Exactly. And the total volume of air inside stays the same, but you've changed its shape. In a similar way, with squeeze states, we can reduce the uncertainty in one property of a particle, like its position, but that causes the uncertainty in another property, like its momentum, to increase.
Wait, so we can manipulate uncertainty itself. Isn't that kind of cheating the system?
Not really. It's more like strategically redistributing uncertainty. It's like playing a game of quantum give and take.
Okay, I think I'm starting to understand how we can fine-tune these quantum states for specific purposes using the displacement operator. It's like we're becoming quantum mechanics. But what about these squeeze states? What are they good for? How do we actually use them?
Squeeze states have a lot of potential applications, especially in areas where we need extremely precise measurements. For example, they're being explored for use in gravitational wave detectors.
Gravitational waves. Those are the ripples in space-time caused by massive cosmic events, right?
Exactly. Detecting them requires incredible sensitivity. And squeeze states can help us achieve that by reducing the uncertainty in certain measurements.
Wow. So by manipulating uncertainty, we can potentially unlock secrets about the universe that were previously hidden from us? That's amazing.
It really is. And it's all thanks to the amazing power of operators, like the displacement operator.
Okay. You've officially blown my mind wide open with all this quantum weirdness. But I have a feeling there's even more to this story, isn't there?
You know there is. There's one more really fascinating aspect of the displacement operator I want to tell you about. It has to do with how we count particles in the quantum world.
Counting particles. I have a feeling it's not as straightforward as just 1, 2, 3.
You're right about that. Quantum counting is a whole different ballgame.
Okay, so how do we count these quantum particles if it's not as simple as 1, 2, 3?
We use something called the number operator.
And the number operator, okay. And what does that do exactly?
It tells us how many particles are present in a given quantum state.
So it's like a quantum counter.
Exactly. But here's where the displacement operator comes back into play. Remember those coherent states we were talking about? The ones created by applying the displacement operator to the vacuum state?
Right, the ones that act like lasers.
Yeah. Well, when we apply the number operator to a coherent state, We get a very specific distribution of particle numbers.
A distribution, what does that mean? Are there like fractions of particles or something?
Not fractions, but it means there's a range of possible particle numbers we could measure, and each number has a certain probability of being observed.
Okay, so it's not like we always get a definite answer when we count. It's more like rolling a dice.
That's a good analogy. The number of particles we measure in a coherent state follows something called a Poisson distribution. It's a statistical distribution that describes the probability of different numbers of events happening randomly over a given time period.
Poisson distribution. That rings a bell from somewhere. Can you give me an example?
Sure. Imagine you're standing at a busy intersection, counting how many cars pass by each minute. Most of the time, you'll see a similar number of cars. But occasionally, you might get a minute with a lot more cars, or maybe even a minute with very few. That's kind of what a Poisson distribution looks like. It describes those variations.
Ah, okay. So in the case of coherent states, the Poisson distribution tells us the probability of finding different numbers of particles when we use our quantum counter.
Exactly. And the displacement operator is what sets up the specific kind of particle distribution in the first place.
Wow, I never thought counting particles would be so complicated. But it's also fascinating to see how these abstract mathematical concepts, like the displacement operator and the Poisson distribution, can have such a profound impact on how we understand the physical world.
It really highlights the interconnectedness of math and physics, doesn't it? They're not separate disciplines, but rather two sides of the same coin, each illuminating the other.
I totally agree. And it makes you realize how much more there is to learn and explore in the vast realm of quantum mechanics. I feel like we've just scratched the surface today.
We have, but hopefully it sparked your curiosity to learn more.
Absolutely. It's been an incredible journey through the quantum world, and I can't wait to see where it leads us next. Thanks so much for guiding us through it all.
It was my pleasure. Keep questioning, keep exploring, and never stop being amazed by the wonders of the universe.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.